Hello, I'm Sapna Davis of ECE Department, Rajagiri School of Engineering and Technology. Next, we are going to discuss about a parameter estimation. We can design an optimal classifier if priori probabilities P of omega I and the conditional probabilities P of x on omega I are known to us. But in many cases, it may not be available. Then we can estimate it from the data samples. Assume P of x on omega I is a normal density with mean mu I and covariance matrix sigma I which are unknown. This simplifies the problem to estimating the parameters mu I and sigma I because we have already assumed the probability distribution. Maximum likelihood parameter estimation. Consider a C-class problem. First, we have to separate the data samples according to the class so that we have C number of sets D1 to DC. Assume P of x on omega j has a non-form with parameter vector theta j. For example, if P of x on omega j has a normal distribution with a mean mu j and covariance matrix sigma j, then theta j consists of a mu j and a sigma j. Now we have to estimate a C number of parameter vectors theta 1 to theta c for every class. We can use a training sample set D drawn from the probability density P of x on theta to estimate the unknown parameter vector theta. Suppose D contains n samples x1 to xn. Since the samples are drawn independently, P of D on theta can be written as a product of a P of xk on theta where k varies from 1 to n. P of D on theta is called as the likelihood of theta with respect to the set of samples. The ML estimate of theta is the value that maximizes P of D on theta. It is easier to work with the logarithm, and also theta that maximizes the log likelihood also maximizes the likelihood. So we can define L of theta as the log likelihood function. So L of theta equal to logarithm of a P of D on theta. If theta is a P component vector, then theta equals theta 1 to theta P transpose and delta theta be the gradient operator, and it is given by dou theta 1 to dou theta P. Solution for theta will be maximizing the log likelihood. That is what is given in the first equation. Then L of theta equation is also given. Here the product term has been changed to summation because of a logarithm. Then the gradient of L of theta is also given. ML estimate for theta can be obtained from the set of P equations. Del theta of L of theta equal to 0. Consider the Gaussian case with unknown mu. Suppose the samples are drawn from a multivariate normal density with the mean mu and covariance matrix sigma. For simplicity, we can consider only the mean is unknown. Then consider the sample point xk and the log likelihood function is as given. The gradient of the log likelihood function is also found. Here the derivative is taken only with respect to mu. We obtain ML estimate of mean as the arithmetic average of training samples. Geometrically, if we think of the n samples as a cloud of points, the mean is the centroid of the cloud. The Gaussian case with unknown mu and sigma. Generally, the mean mu and the covariance matrix sigma will not be known to us. Then these two parameters will be constituting the parameter vector theta. We can consider the univariate case with the theta 1 equal to mu and theta 2 equal to sigma square. Then the logarithm of the likelihood function is given and the derivative with respect to theta 1 and theta 2 are also given. Setting the gradient of L of theta equal to 0, we can solve for theta 1 and theta 2. Then we get mu equation and the sigma square equation. And for the multivariate case, we get the covariance matrix equation. ML estimate for the mean vector is the sample mean. And the covariance matrix is the arithmetic average of the n matrices. ML estimate for the variance sigma square is biased. That is, the expected value of the sample variance is not equal to the true variance as shown. Expectation maximization algorithm for a parameter estimation. Suppose some of the training points are missing features. Consider a sample set D equal to x1 to xn taken from a single probability distribution. Any sample point can be written as a xk equal to xkg and xkb, that is comprising of both good features and bad or missing features. We can separate these individual features into two sets dg and db such that D equal to dg union db. Next, we can form a function as given. On the RHS, expected value is over the missing features. The parameter theta is the current estimate and theta is a candidate vector for an improved estimate. Given such a candidate theta, the equation will be calculating the likelihood of the data with respect to the current distribution theta I. Algorithm will select the best theta, that is theta I plus 1, the one which is corresponding to the highest value of the Q function. I is the iteration counter and T is the convergence criterion. We begin with the initializing theta 0 and T, and also I is set equal to 0, and in every step it is increased by 1. And the expectation step is to compute the Q function, and at the maximization step, next theta value is found such that the Q function is maximum. And this is repeated till the difference between the current Q function and the previous Q function is less than the threshold. And the corresponding theta is returned as the final theta. The explanation is given here. The EM algorithm starts with some initial value of the parameters theta 0. Then via the M step, the optimal theta 1 is found. Next, theta 1 is held constant and the value of theta 2 is found, which optimizes the Q function. This process is repeated till no theta can be found that will increase the Q function. Feature extraction and the dimensionality. Every feature is useful for some discriminations. Also, features can provide independent information and every feature contributes to reducing the probability of error. There are two issues to be considered. First one, how the classification accuracy depends upon the dimensionality or number of features, which will be further deciding the amount of training data. And second one is the computational complexity of designing the classifier. Higher the dimensionality, larger will be the computational complexity. In general, if the performance obtained with a given set of features is inadequate, add new features which may increase the cost and complexity. Computational complexity of an algorithm is given in terms of the number of mathematical operations such as additions, multiplications and divisions, or the time and memory needed on a computer. Curse of dimensionality. The demand for a large number of samples grows exponentially with the dimensionality of the feature space. If we have more features than observations, that overfits classifier model. When we have too many features, observations become harder to cluster. While measuring the Euclidean distance, every new dimension adds a non-negative term to the sum, so the distance increases with the dimensionality for input vectors. Hence, as the number of features grows, the points in the feature space become sparse. Next, we'll see overfitting. Figure shows a set of 10 data points and two proposed curves for fitting them. The data points were actually obtained by adding zero mean independent noise to a parabola. So a parabola would provide the best fit. Even a straight line can fit the training data fairly well. The 10th degree polynomial fits the given data perfectly, as you can see in the figure. But a 10th degree polynomial is not required here because it leads to overfitting and the generalization performance degrades. So we can begin with a higher order polynomial, maybe 10th order, and successively simplify the model by eliminating the higher order terms. So this will increase the error on the training data, but generalization performance will be improving. Fisher's linear discriminant analysis. It is used for dimensionality reduction. First, we'll begin with a two-class problem. Take the d-dimensional input vector x and project it down to one dimension using y equal to w transpose x. Set a threshold on y and classify x as follows. If y greater than or equal to minus w0, assign x to class C1, else class C2. And then we get a linear classifier. Projection onto one dimension causes loads of information, so classes well separated in the d-dimensional space may overlap in one dimension. By adjusting the weight vector W, we can maximize the class separation. Figure shows two classes well separated in 2D space overlap when projected onto the line joining their means. Let there be n1 points of class C1 and n2 points of class C2. Mean of the two classes are given. A simple measure of separation after projection is the distance between the projected class means. We have to choose W so as to maximize this distance given by M2 minus M1. The projected mean can have a large value if W is large. So constrain W to have unit length such that summation Wi square equal to 1. perform constrained maximization using a Lagrange multiplier, then we get a W is proportional to M2 minus M1. Fisher's idea is to maximize a function that gives a large separation between the projected class means while giving a small variance within each class, and this will be minimizing the class overlap. The within class variance of the projected data of class CK is given in the equation, where Yn is the projected data and Mk is the projected mean. The total within class variance for the whole data is S1 square plus S2 square because it's a two class problem. The Fisher's criterion is the ratio of the between class variance to the within class variance and is given by G of W. In the first equation, M2 and M1 are the projected class means and the second equation, SP is the between class covariance matrix and SW is the total within class covariance matrix, which are defined in the respective equations. Differentiating with respect to W, JW is maximum when the following condition is satisfied. SPW is always in the direction of M2 minus M1. Magnitude of W is not important, only its direction. So drop the scalars W transpose SPW and W transpose SWW. Multiplying both the sides of the equation by SW inverse, we get W is proportional to SW inverse M2 minus M1. This is known as the Fisher's linear discriminant, a direction for projection of the data down to one dimension. For classification, choose a threshold y0 and a new point is classified as belonging to C1 if yx is greater than or equal to y0, else to C2. Now consider the case with the more than two classes. We can define y as a W transpose x as before. Let nk be the number of points in class Ck. Then n equal to summation nk is the total number of data points. In the projected space, we can define the within class variance and the between class variance as before. Here the summation is for k number of classes and mu k is the mean of the kth class in the projected space and mu is the overall mean in the projected space. Construct a scalar that is larger when the between class covariance is larger and within class covariance is small. One choice is G of W equal to trace of SW inverse SP. This criterion can be rewritten as a function of W as given. Principal component analysis. It is also known as a KL transform and it's used for a dimensionality reduction. PC is the orthogonal projection of the data onto a lower dimensional space such that the variance of the projected data is maximized. Maximum variance formulation. Consider a set of n data points with a dimensionality d. Now the requirement is to project the data onto a space having dimensionality m which is less than d while maximizing the variance of the projected data. Consider the projection onto a one-dimensional space that is m equal to 1. Define the direction of the space using a d-dimensional vector u1. Choose it to be a unit vector so that u1 transpose u1 equal to 1. Each data point xn is projected onto a scalar u1 transpose xn. The mean of the projected data is u1 transpose x bar, where x bar is the sample set mean, and the variance of the projected data is u1 transpose su1, where s is the covariance matrix. Maximize the projected variance u1 transpose su1 with respect to u1. This is a constraint maximization because u1 transpose u1 equal to 1. Then introduce the Lagrange multiplier lambda and then maximize u1 transpose u1 plus lambda 1 1 minus u1 transpose u1. Set the derivative with respect to u1 equal to 0. We get su1 equal to lambda 1 u1. So u1 is an eigenvector of s. Multiplying both the sides with the u1 transpose, we get u1 transpose u1 equal to lambda 1. So variance will be maximum when u1 is the eigenvector having the largest eigenvalue lambda 1. This eigenvector is known as the first principal component. Consider the general case of m-dimensional projection space. Optimal linear projection is defined by the m eigenvectors u1 to um of the data covariance matrix S corresponding to the m largest eigenvalues lambda 1 to lambda m. PC evaluates the mean x and the covariance matrix S of the data and then m eigenvectors of S corresponding to the m largest eigenvalues. Minimum error formulation. Now the requirement is to project a d-dimensional data point xn onto m-dimensional space where m less than d. Consider an orthonormal set of basis vectors ui where I varies from 1 to d that satisfy ui transpose uj equal to delta ij. Every data point is given by a linear combination of the basis vectors as given, where alpha n1 to alpha nd represent the components of xn, xn1 to xnd. Now alpha nj will be equal to xn transpose uj, which can be replaced in the xn equation. The m-dimensional subspace can be represented by the first term basis vectors, and so every data point xn can be represented as shown, where z and I depend on the data point and bi are constants, same for all data points. So we have to choose ui, z and I and bi to minimize the distortion due to dimensionality reduction. Average of the square distance between the original data point xn and its approximation can be used as a distortion measure, which is given by j. Now minimize j with respect to z and j. Set the derivative of j with respect to z and j to 0, and from the orthonormality conditions we get z and j equal to xn transpose uj. Set the derivative of j with respect to bj to 0, we get bj equal to x bar transpose uj. Then the displacement vector from xn to xn approximation, which is given in the equation as xn minus xn approximation, lies in the space orthogonal to the principal subspace because it's a linear combination of ui where I varies from m plus 1 to d, which is shown in the figure. J as a function of ui is given. Minimizing j with respect to ui is a constrained minimization due to orthonormality conditions. Consider a two-dimensional data space with a d equal to 2 and a one-dimensional principal subspace with a m equal to 1. Choose the direction u2 to minimize j equal to u2 transpose s u2 subject to the constraint u2 transpose u2 equal to 1. Now using a Lagrange multiplier lambda to minimize j approximation equal to u2 transpose s u2 plus lambda to 1 minus u2 transpose u2. Set the derivative with respect to u2 to 0, we get s u2 equal to lambda to u2. So u2 is an eigenvector of S with eigenvalue lambda 2. J will be minimum if u2 is the eigenvector corresponding to the smaller eigenvalue. So the principal subspace will be aligned with the eigenvector with the larger eigenvalue. In general, J can be minimized for arbitrary D and M by choosing ui to be eigenvectors of the covariance matrix. Then the corresponding distortion measure is j equal to summation I equal to m plus 1 to d lambda I. That is the summation of the d minus m smallest eigenvalues. The eigenvectors defining the principal subspace are those corresponding to the m largest eigenvalues.